Welcome to lecture 22 of the course Marine Propulsion. Today we will continue with propeller model tests. So, the points covered in today's lecture will be a self-propulsion test of a marine propeller, a demonstration experiment from our facility showing the self-propulsion test in the towing tank, and calculation of propulsion factors from the results of self-propulsion test, in addition to the results from the resistance and open water tests. With regards to model tests for ship powering, the three tests which are required to do the powering calculations for a ship are the resistance test, the open water test which have been discussed in the last class, and the self propulsion test which will be discussed today. So, we have the results from these three tests which are used together to calculate the propulsion factors and finally do the powering calculations for the ship. In addition to this, in general for naval architecture there are other tests like sea keeping tests in waves and maneuvering tests which are done for models for assessing the performance of a vessel in waves and also for the maneuvering performance of a vessel. These tests which are mentioned here are specifically used for ship powering and hence are discussed in this particular course. Now, for the self propulsion test, the objective is to determine the performance of the propeller and ship hull when working together at specific design conditions. That means, how the propeller performs behind the ship, and using that we try to estimate the propulsion factors, and as we have earlier discussed that the propeller performance is different in open water and behind hull conditions, because the ship modifies the flow into the propeller and that changes the propeller thrust and torque characteristics and efficiency. And then the resultant parameters which are the hull propeller interaction parameters we can say, or the propulsion factors, which includes wake fraction, thrust deduction, relative rotative efficiency can be calculated, and from there finally we want to calculate the delivered power and revolution rate of the ship propeller for different speeds. So, in today's lecture we will look into the first 2 points of this self propulsion test. So, how to do a self propulsion test and how to calculate the parameters which relate to the propulsion coefficients, and in the next class we will use this to estimate the delivered power and RPM of the ship propeller in the full scale. So, when the model moves at a constant speed due to the propeller thrust alone, that condition is called the model self propulsion point. Till now we have seen that in the open water test the propeller was only moving ahead at a particular speed which was the advanced speed, and there was no ship hull. So, it was connected to the carriage and it was moved at a particular forward speed. Here in the self propulsion test we have the ship and the propeller together. So, the ship is towed by the carriage and the propeller is also rotating to provide a thrust, and if the propeller thrust is good enough to move the ship at that particular constant speed, then it is called the model self propulsion point. Now, this exactly does not represent the actual conditions for a ship. The understanding of this particular point is very important for a self propulsion test. The self propulsion point of the model is not equal to the self propulsion point in the full scale or in the ship scale. Why? Because we have done fruit scaling. We have seen that when we have discussed similarity, we have maintained fruit scaling between the model and full scale. That is, we have maintained the ratio of the inertial force by gravity force. So, in order to maintain that, we have got similar wave making pattern in the model and full scale, where the length with respect to the velocity is scaled. Now, we see that the Reynolds number will be very much different in the model and full scale, and because of that the viscous effects will be very much different. And in the resistance test, we know that the skin friction coefficient is different in the model and full scale. So, there is a separate scaling involved for the skin friction drag for the ship based on ITTC procedures, which is used for resistance scaling from the model to the full scale. Now, because of that, the propeller loading at the propulsion point will be different in the model and full scale, because the Reynolds number is very much different, and also there are other factors like roughness is different in the model and full scale. So, because of these reasons, we have to make some corrections so that the ship self propulsion point is obtained in the model scale to adjust the propeller loading such that it operates at the ship self propulsion point, not the model self propulsion point, because we have to calculate the propulsion factors corresponding to the self propulsion point of the ship. So, because of these factors, the total resistance coefficient of the ship is not equal to the total resistance coefficient in the model. Now, due to difference in Reynolds number and roughness between the model and full scale, a skin friction correction force, which is denoted as FD, is required to be calculated. Now, FD is related to the difference in friction resistance coefficient between the model and full scale as per these expressions. So, FD is defined as a coefficient Cs multiplied by half rho s v square, where s with suffix m is the weighted surface area of the model and Vm is the model speed. Now, this coefficient Cs is given by 1 plus k, where k is the form factor, into Cfm, which is the friction resistance coefficient in the model scale, minus the same in the full scale, and a roughness allowance is also included. So, this skin friction correction force is required to be calculated to get the full scale propulsion point when we do the model self propulsion test. This part is very important because this force has to be applied on the model and that correlates to the full scale self propulsion point. Now, Cf can be calculated simply using ITTC 57 ship model correlation line, and this is based on the Reynolds number as we have seen in standard resistance calculations, and delta Cf, which is the roughness allowance, is also given by ITTC based on this formula. Here Ks is the roughness of the hull surface in the full scale ship, and if the value of Ks is not known, ITTC recommends this particular value to be used for the calculation of delta Cf, which is the roughness allowance. Now, this skin friction correction force is including the differences of friction resistance coefficient between the model and full scale, and also the effects of roughness of the full scale ship. In later revisions of this skin friction correction force, ITTC also included correlation allowance. This allowance depends on the correlation of model test results in the model scale for the self propulsion test with the values obtained for sea trials. So, these correlation allowance depends on the facility where the model tests are being carried out, and they can also be included in the skin friction correction force, which was mentioned in the later revisions. So, this skin friction correction force FD is applied as an external tow force on the model in the self propulsion test. Why? It is done to obtain the ship self propulsion point on the model. So, we are doing a model test in the model scale, but we would want to get the propeller loading corresponding to the ship self-propulsion point, because it is the point at which the propeller coefficient should be calculated and the ship powering should be done. So, because we cannot maintain the Reynolds number same between the model and full scale, and also to have the effect of the roughness, the skin friction correction force is calculated and it is applied as an external tow force. So, it gives the theoretically correct propeller loads during the self propulsion test, which is corresponding to the full scale propulsion. Now, the self propulsion test can be done typically using two standard methods. The first method is the continental method. Here the model is towed using the carriage, and when a steady speed is reached, the model is released, and we maintain the propeller RPM and adjust it in such a way that the model achieves the same speed as the carriage, and the force which is calculated FD, the skin friction correction force, is applied by a weight using a pulley system. So, at this particular ship self propulsion point, which corresponds to this calculated value of FD, we are adjusting the propeller RPM so that the speed of the model is equal to the speed of the carriage, and at this balance point the propeller thrust, torque and RPM are measured using a propeller dynamometer. So, for this particular method we use only one run for each vessel speed. So, for a particular model speed we measure the propeller RPM, thrust and torque using the dynamometer, and this corresponds to a particular value of tow force as provided by the pulley system, which is calculated based on the skin friction correction force FD, and this gives the self propulsion point corresponding to the ship scale in the model test. In the other method for self propulsion test, which is also called the British method, we vary the propeller RPM. So, the model is towed using the carriage which is on the towing tank, and for a fixed carriage speed the propeller RPM is varied, and the model is connected to the carriage using the resistance dynamometer, and for varying RPM of the propeller the force exerted is the tow of force, and it is measured by the resistance dynamometer, and apart from that the propeller thrust and torque are measured using the propeller dynamometer. A demonstration of this in our facility will be shown just after this slide. So, here instead of a specific RPM, the propeller RPM is gradually varied in steps, and for each case the tow of force or the force exerted at the resistance dynamometer is measured, and the value is varied in steps in such a way that the model operates in both underloaded and overloaded conditions. That means, we try to achieve the self propulsion point in the full scale at that condition where F tow, this force will be equal to FD, which is the calculated skin friction correction force corresponding to the full scale ship self propulsion point. So, the value of the RPM of the propeller N here is varied in such a way that the tow force is both lower and higher than the required FD or the skin friction correction force. Now, the required value of RPM at the value of the tow force equal to FD or the self propulsion point in the ship scale is calculated by interpolation. So, at least 3 to 4 runs are taken covering the self propulsion point, and by interpolation we can calculate the self propelled RPM, and at that RPM the thrust and torque values are also obtained from interpolation. Let us look into the diagrams for the two different methods. First, we have the continental method for the self propulsion test. Here we have the ship model fitted with a propeller, and the propeller is connected via a shaft to the dynamometer and the motor. The motor is giving the required RPM to the propeller and the dynamometer measures the propeller thrust and torque. And the model is connected to the towing carriage here, and the carriage is towing the model along the towing tank. Now, the friction correction force FD is exerted with the help of a weight and a pulley system on the model. So, in this particular method, the exact self propulsion point is considered by applying the value of the calculated skin friction correction force as the tow force on the model using the pulley, and the propeller is running at the specific RPM which propels the ship forward at that specific speed, which is the model speed, the fruit scaled version of the full scale ship speed. The next method is the British method, which is also called load varying propulsion test. Here the model is connected to the carriage through a resistance dynamometer, and the model is towed by the carriage at a specific model speed, which is the fruit scaled version of the ship speed, let us say for the design condition, and the RPM of the model is gradually varied in steps. So, we have the RPM gradually increasing, and as the RPM increases, the requirement of the tow force will be less. So, the tow force is exerted by this resistance dynamometer, and from multiple readings we can do interpolation to get the self propulsion point where the tow force is equal to the skin friction correction force. That will be the full scale ship self propulsion point on the model. And here also we have the motor which is providing the RPM to the propeller here, and we have the rudder behind the propeller for the self propulsion test, and the dynamometer is measuring the propeller thrust and torque. Next, we will see a video of this British method of self propulsion test from the towing tank facility at IIT Kharagpur. This is the self propulsion test in the towing tank, where the carriage is moving on the tank and it is towing the ship model with a propeller fitted behind, and the model is connected to the carriage through the resistance dynamometer. The model is ballasted with these weights to the required draft, and we have the resistance dynamometer here which is connected to the model. These weights are distributed along the length of the model to achieve the desired draft. This is the self propulsion test condition, where we have the motor and the dynamometer which is connected to the propeller shaft, and we have the propeller which is behind the ship rotating here, and the rudder behind the propeller. This is a video of the underwater part, where the propeller RPM is provided and the ship is moving forward in the self propulsion test. So, for this specific model, the propeller is on an inclined shaft, and here the model is being towed with the propeller rotating behind at a specific speed. And for each model speeds, we will have different sets of propeller RPM increased in steps, so that we achieve the self propulsion point by interpolation as discussed. Now, here the speed of the model is increased, and that is why the wave making pattern is very much different. So, this is the highest Froude number for which it was tested, and that is why the wave making pattern is different when we increase the Froude number of the vessel. So, in this way we have different runs of the model along the tank. For each run, the speed is kept constant and the propeller RPM is increased in steps to achieve the self-propulsion point. So, we have the model ship which is propelled with the help of this propeller providing a thrust T, and we have the resistance dynamometer here which is providing a tow force which is connected to the carriage. It is moving forward at a specific speed. Now, this propeller itself is connected to a propeller dynamometer and a motor, which propeller dynamometer is measuring the thrust and torque of the propeller. Now, for a specific model speed Vm at which the model is moving forward, we increase the RPM of the propeller in steps. The rudder is not shown here for convenience, and here as the propeller RPM is increased, the thrust from the propeller will increase. Now, in all these different RPM conditions, the model speed is constant, which is Vm. So, when the propeller thrust is very low, let us say we have 4 different RPMs on a specific run, N1, N2, N3 and N4 in increasing order. Okay. So, when we have the lowest RPM N1, then the thrust contribution from the propeller will be very low, and as the RPM increases, the propeller thrust will gradually increase. Similarly, the tow force which is exerted from the carriage on the model to tow the model at a specific speed should gradually decrease. Let us say F tow 1, F tow 2, F tow 3 and F tow 4. So, for the case where the RPM is N1, lowest RPM, the tow force will be highest because the propeller thrust component is low, and gradually the tow force will decrease, and we have to capture the self propulsion point where the tow force F tow is equal to the skin friction correction force Fd, which should be somewhere in between these 4 points. Now, if we plot the propeller thrust versus RPM, it will increase as the RPM increases. On the other hand, if we plot the tow force, F tow with RPM, the tow force will decrease with the increase of RPM. Now, let us say these are the 4 points N1, N2, N3 and N4. Now, at the point where the tow force is 0, what is the physical meaning? When there is no tow force required to tow the model, the thrust is enough for the model to be propelled. That is the model self propulsion point. That means the model itself is self propelled. But it is very important to remember that this is not the ship self propulsion point that we are interested in, because the ship powering has to be done in the ship self propulsion point. That is why we have calculated the skin friction correction force Fd. So, we have to take the point where the value of tow force is equal to Fd, this point. So, let us say Fd has a value here. Now, if we do an interpolation, then we can get this particular point and calculate the value of RPM at that particular point. Now, this is the ship self-propulsion point. On the model. So, this particular value of Fd, when the tow force is equal to Fd, that gives the ship self-propulsion point on the model as we have discussed, and the RPM corresponding to that gives the correct propeller loading for the self-propulsion test. Okay. Now, N4 in this case gives a negative tow force. Now, what is the meaning of negative tow force? That means the model is over propelled. The propeller thrust is already good enough. When the tow force is 0 at this point, then the propeller thrust is already enough to propel the ship, and if we still increase the RPM, then the propeller will produce more thrust than actually required to propel it, then the tow force here will be negative. Okay. Now, the points are taken in such a way that the self-propulsion point can be obtained using interpolation. This is how the self-propulsion point is defined with respect to the thrust and the tow force, which is used for the calculation of propulsion factors from the model test. This flow chart shows the data acquisition system from different parts of the self-propulsion test setup as per standard ITTC recommended procedures for model self-propulsion test. We have the carriage which is towing the ship model fitted with a propeller. In the carriage, we have the speed measurement system which measures the model speed. Next, on the hull model, we have the resistance dynamometer which is measuring the resistance or the tow force in this case. We also have a sinkage and trim measurement system because the model in a standard self-propulsion test should be free to sink and trim. So, this sinkage and trim during the tests is measured. Now, if we move on to the propeller, we have the propeller dynamometer which is connected to the propeller and it measures the thrust, torque and RPM of the propeller. And finally, we have the environmental factor which is the temperature measurement which is done to calculate standard density and viscosity of water during the model tests. So, all these data together is put into the data acquisition system and finally put into the computer for final calculation of the self-propulsion test parameters. Now, if we look into the calculation of the propulsion factors, we have the resistance test which has been done before. We have the propeller open water test which was done with only the propeller. We have the self-propulsion test which is done for the ship model with the propeller working behind it. Now, what is the output of the resistance test? We have the total resistance of the model. From the self-propulsion test, what are the measured values? The propeller thrust, RPM and propeller torque. Now, using the resistance that we calculate from the resistance test, the total resistance and the propeller thrust from the self-propulsion test, we use the value of Fd which is the skin friction correction force to get the thrust deduction. which is the propulsion factor, one of the important factors which is required for the calculation of ship powering. The next is the use of the thrust and torque obtained from the self propulsion test. We use the data of the open water test to calculate the wake fraction, so here it is written as Wt, which represents the wake fraction calculated using thrust identity. We have discussed about thrust and torque identities and how to apply them to the open water diagram. We will again go into these calculations in brief in the next slides. And the other propulsion factor here is the relative rotative efficiency, eta r. So, in this way we can use the resistance and self propulsion test along with the open water test data to calculate the propulsion factors which will be required for ship powering. Now, for the thrust deduction, this part is very important to understand that as we have previously written this particular expression, the thrust deduction is related to the total resistance from the resistance test and the thrust measured from the propulsion test at the model self propulsion point. That means where the tow-rope force is 0. So, there is no correctional force. But when we apply the skin friction correction force, the self propulsion point is shifted from the model self propulsion point to the ship self propulsion point, and here the thrust deduction factor will include Fd, which is the skin friction correction force in its expression. So, we have, let us say, we have the ship model which is towed in the self propulsion test, and at the resistance dynamometer we have a tow force which is Fd, okay, which is the skin friction correction force. The thrust provided by the propeller is T, and we know that RT is the total resistance of the model obtained from the resistance test. And we have seen earlier that in hull propeller interaction part of this course that this RT will increase because of the suction effect of the propeller. So, the resistance test value that we get, the total resistance that we get from the resistance test will be increased slightly when the propeller is acting behind the ship. So, in the self propelled condition the resistance will be increased, and we take care of that not by an increase of delta r, but by an equivalent decrease of the thrust by an amount delta t that we have seen. And to balance for that we write T as T minus delta t, okay, because we are balancing these values T and Fd with the resistance measured during the resistance test. We have to account for that using a factor delta t, which is the thrust deduction, and this is mentioned as 1 minus t, where small t is the thrust deduction factor, right. So, we can write finally T into 1 minus t plus Fd is the total force in the forward direction should be equal to the RT when the model moves forward at uniform speed. So, this gives 1 minus t equal to RT minus Fd by t, which gives t equal to 1 minus RT which is this equation. So, the thrust deduction factor during the self propulsion test can be calculated using the total resistance from the resistance test and the thrust from the propulsion test using the value of Ft. So, let us simply look into the calculation of all the propulsion factors together, and this will be the summary, which is the combination of the self propulsion test along with the results obtained from the resistance and open water tests. So, the output of the self propulsion tests are the propeller thrust, torque, propeller revolution rate and speed of the model, represented by T, Q, N and V in the model scale. So, using the resistance and toe force values, we can calculate the thrust deduction as we have just seen using this equation. Now, from the measured value of thrust and torque, we can calculate the thrust and torque coefficient in the behind hull condition for the propeller. Now, we will use this data to enter into the open water diagram, which we have obtained from the propeller open water test. As we have previously discussed, there are two ways of entering into the propeller open water diagram. One is using the thrust identity and another is using the torque identity. So, both of these are shown, and J is the advance coefficient, which is given by VA by ND. And using thrust identity, we use KT calculated from the self propulsion test to enter the open water diagram here, and we can get the corresponding value of J. And if we try to use torque identity, we use KQ measure from the self propulsion test to enter into the open water diagram and get the value of J. And as we have seen earlier, that the value is slightly different in terms of the obtained J and N when we use thrust and torque identities. Now, a simple example is shown here. Using thrust identity, we can calculate the wake fraction first. Let us say we enter the open water diagram using KT and obtain the value of J. Now, the wake fraction now can be calculated by this equation, where N, D and V are obtained from the self propulsion test and J is the value which is taken from the open water diagram. Next, we can calculate the relative rotative efficiency. Since we are using thrust identity, relative rotative efficiency is given by eta r is the ratio of KQO by KQ, where KQO is the torque coefficient obtained from the open water diagram and KQ is the torque coefficient in the self propulsion test. And finally, we can calculate the hull efficiency eta h by this equation, 1 minus thrust deduction factor by 1 minus wake fraction. Now, this wake fraction is called the effective wake fraction, as opposed to the nominal wake fraction, which we had measured behind the ship hull. Now, in the wake measurement tests, one can use different ways to measure the wake velocities behind the ship hull and get the average velocity on the propeller plane without the presence of the propeller. So, it is the averaged value of the velocity at the plane of the propeller measured behind the ship hull, but without the presence of the propeller itself. Now, when the propeller is acting behind the ship hull, it also changes the flow in the stern part of the ship. Now, it cannot be measured directly from the experiment because the propeller is rotating at that particular position. Because of this, there is an indirect way which we call the effective wake fraction. We use this value of self propulsion tests and combine it with the open water test values. So, we enter using thrust and torque identity as just shown, and we get the effective wake fraction, which is a representation of the velocity of advance of the propeller when it operates behind the ship hull. So, this is the standard representation of the propulsion factors calculated from the self propulsion tests in combination with the results obtained from resistance tests and open water test. So, this will be all for today's class. In the next class, we will go into the calculation for the ship powering using the results of model self propulsion test. Thank you.